In this tutorial video, we're going to present you with a problem and then show you how to solve it. And the purpose of this is to give you some idea how to apply what you're learning in the course. So, here we go. Here's the problem. A cylinder is rolling without slip on a horizontal surface. It's connected to the wall with a spring of constant K. In the presence of gravity, the cylinder has radius r and mass m and a moment of inertia I sub c, where the moment of inertia is measured with respect to the center of mass. And what we want to do is find the equation of motion. So the first thing we do is assign generalized coordinates. We have x, the translation, in the horizontal direction, and theta, the rotation of the cylinder. An often overlooked point is that these arrows are very important. They designate the direction of positive value of the coordinate in question. They also designate the reference. And in this case, we assume that both x and theta are 0 when there is no force in the spring. First question we have to answer, how many degrees of freedom? It might look like there are two, x and theta, but in fact they are related by the no slip condition. We have the kinematic constraint that x equals r theta. So these two are related. Next, we have the free body diagram. The weight of the cylinder, mg, directed straight down. The normal force, N, from the ground to the cylinder. The unknown friction force, F, the force from the spring, F sub K, and the moment of inertia, the external applied moment, M. Then we apply Newton's law, summing forces in the x direction we have the friction force to the right, the spring force to the left, sum to equal mx double dot. Summing forces in the y direction, we have N we have the normal force vertical, the weight going down, and equals my double dot, which is 0. Now summing torques or moments about point C, we have m minus r sub f equals the moment of inertia times theta double dot. Okay, with these three equations, now let us undertake to eliminate the unknown friction force. So from the first equation, we will simply rewrite this such that F, the friction force, is equal to mx double dot plus F sub k. And so we'll then substitute that into the third equation. The third equation looks like this. So substituting that in, so now let us make a substitution for F sub k. Let's make two substitutions. One, we know that F sub k is equal to k times x, and the other is our kinematic constraint. This kinematic constraint survives differentiation. So now, substituting these, we have m minus mr x double dot, which is r theta double dot, minus r times f sub k, which is k times x, which is r times theta, is equal to I sub c theta double dot. Now let me simply rearrange this. And one more time, one small rearrangement. And there you have the answer. A conventional second order differential equation in theta. You can see the moment of inertia term. This is the moment of inertia about the center of mass plus mr squared, theta double dot, and this is the spring term. So there you have it.